Okay, so this week we have five problems again, and I'd say that the first two are sort of random questions that hopefully are still interesting, and then the last three are specially chosen for illustrating feelings about data structures that maybe you haven't thought about before, even if you have seen the standard data structures before. Um, so let's talk about these problems. And I will start with the first one. Again, I'm assuming that you have read the problem. Um, so anyway, you got up to 300,000 numbers. Each number is up to a billion positive numbers. And the idea is that you want to drink water, maximum amount of water you can drink. So how do you drink? So in here, if you have five numbers, you can choose to drink in whichever day you want to drink. But as soon as you drink five from the first day, for example, then every single day after that is subtracted by five. So it will become -2, -3, 4, and 5. And you can, if you decide to drink on a certain day, you must drink all of it, and you can only drink if it's not negative, right? Um, so you don't have to drink on a certain day. And in this case, for example, you could drink on, what do they say? You can drink on the second day. So skip the first day, drink 3. Now everything after that is -3. So this is -1, so you can't drink. And then you have 6 and 7. And then you decide to drink 6 from here. And then the 6 and the 7 becomes a 1. And then you can drink the last one for a total of 10. And the question is, what is the maximum amount you can drink in total? And because they're up to 300,000 numbers, um, you can just try all possible ways for every single day, whether you drink or not drink. Now, this is a problem that was originally used in some kind of, I guess, I don't know if this is like a high school challenge or something that's a little bit easier for EMAP people that have a little bit more or less experience. So they have these partial scoring that, um, instead of just saying yes or no, whether you solve it or not, they have some partial scoring that you can get 19 points out of 100 if you solve it for relatively small problems, and then you get 29 more points if you solve it for slightly bigger, and then 52 points, the remaining 52 points if you can solve everything. Okay, so let's take a look at what's happening. So you have a bunch of numbers, a 0, a 1, a 2. Again, my writing tablet is a little bit laggy. Let me try to disconnect it and connect it again and see if that helps. Is it connected now? Okay, let me try to pair it again. Okay, that's connected. Okay, this is better. All right. Now imagine that somebody tell us which days we're gonna drink. Let's say it's these 3 days. Okay. Now if somebody tells us that these are the 3 days that we drink and we don't care about any other days, we could just pretend that these other days don't exist, right? Now, of course, you don't know that this is the answer, but let's just see what happens. So, because we can pretend that the other days are not there, we might as well just assume that we have a sequence where we drink every day. Okay, so I'm kind of showing you how we simplify some of the thinking to make things a little bit easier to understand. Okay, so let's just say that we have a few numbers and we can drink every day. Okay, so if we drink the first day, then we drank A0, right? So we drank it. But now everybody is going to be reduced by A0, right? And then the next day we drink this, so we add to it A1 minus A0, and everybody else will be subtracted by what we just drank. Okay, now what does the total look like? The A0 cancels out, and the total is just A1. And here you can see that after you remove the brackets, A0 also cancels, and it's just like this. The fact that you drank A0 doesn't even appear, right? It's as if you never bothered to drink A0, you just start with drinking A1. It's exactly the same thing. And you can carry this out and you will realize that no matter how many more you drink, by the time you drink A2, well, actually, by the time you drink A2 minus A1, it's when you do the calculations, the total will be just A2, and everything would just be adjusted to something minus A2 as if A1 never appeared. Okay, so what is going on here? What is going on here is that it actually doesn't really matter the sequence of days that you drank anything. The only thing that matters is the last day that you drank. That's it. Okay, when you decide to drink, you could have drank on that day, or you could have taken a sequence of days before to drink up to that point, but the net effect is exactly the same. It's just this one is the final answer. So what does that actually mean? If you have a sequence, a longer sequence where you don't know which days you're going to drink, we are saying that the only thing that matters is the last day that you decide to drink. And if you want to maximize this, what should you do? You want the last day to be the maximum of the sequence. And that's all there is to it. So you have to think a little bit about what's going on. And at the end of the day, all you have to do is take the sequence and ask for the maximum. And that's the answer. So here's my solution. It's not very fancy. Read in n, create a vector of that size, read in the input into the vector. So if you're not familiar with what I'm doing, I'm creating a vector of size n. So I'm not, so let me just explain what this is and then I'll tell you what I'm not doing. So I create a vector of size n. I read it in using a range-based for loop, but I have to pass it by reference because a range-based for loop, if I don't use a reference, it will not allow me to change the element of the container. And then I use the STL function max element, which will look at a range. So in this case, the vector, the entire vector, and return an iterator that points to the maximum element. So it does not return the maximum element, it returns an iterator that points to it, which is why I put a star, and that will print. What I'm not doing is to create an empty vector and then keep pushing back. The reason is that every time you push back, there's a possibility that it has to actually reallocate and copy, and that incurs like overhead. Every time you have to resize a vector, there is quite a bit of overhead of reallocating array, getting rid of the old array, copying the old array. Actually, I did it in the wrong order. Reallocating new array, copy the old elements to the new array, getting rid of the old array. So if you knew the size of the vector, you should always allocate the right size and then use it as opposed to trying to push back every step because that can cause big slowdown. Other than that, there's not much more to say, but I guess I do want to show you things like max element, min element, those things. It should be in your back pocket that you can just pull out anytime. Of course, you can always write your own loop to find a max, but it's much better if you know how to use the STL, the standard library. Okay, next one. What's your step? Okay, so again, I'm going to assume that you have read the problem. Basically, you have a grid. You can only go right or up. And you have a start, you have an n coordinates, and then there are two coordinates, two places that you're not allowed to go. And you have to count how many ways you can do this. Right? So you have a grid, you have some starting point, and you have some ending point. You can only go up, you can only go right, and then there are some mines here that you're not allowed to touch. Okay, so perhaps the first question is, what if there are no mines? Right? So what if there are no mines? This is a very classic problem that I've even seen asked in the Math 30. Uh, well, I guess it would be Math 30 dash whatever it is. I don't know which one in the diploma exam. I've seen it. I've seen it asked when I was a student in Math 30 before they have dash one and dash two. But anyhow, um, so what? Okay, so there are certain distance. I'll just call it horizontal distance and a vertical distance. And basically, in total, the number of steps must be h plus v, right? Because you have to go either up or right and up and so on. But eventually, to make it all the way to the end, you must make v vertical steps and h horizontal steps. The only question is, in what order do you do this in? So the total number of steps must be this. There must be h horizontal steps and v vertical steps, right? And in fact, any sequence of the right number of h and v's will get you to the end. And so we're just asking, how many ways can you write a sequence of h and v's so that they're exactly h horizontal moves, v vertical moves, and um, total, of course, is h plus v. And this is pretty classic combinatorial thing because you have h plus v spots. Each of them you have to decide to do the horizontal move, and then the remaining ones are fixed, right? If you decide not to do the horizontal moves, they must be vertical moves. So these two are equivalent, and the answer is just that if there are no mines. Now immediately there's a problem. I hope you see that there's a problem. What is the problem? The problem is that the distance in horizontal distances and vertical distances, because the coordinates are between 0 and 128, h and v can be up to 128. So here it can be up to 256. And of course, here it can be up to 128. And if you know anything about binomial coefficients, it is largest when you have n choose k where the k is exactly half. So anyhow, how big is it? Right? What's 20? What is this? Now the question is, I guess the question is, do you know your binomial coefficients? If you do, and have some feeling about how big these things grow, that you might realize that this is gigantic. How big is 25, 256, choose 128? Okay, 5.76 times 10 to the 75. This is way, way big. Okay, 10 to the 75. Even if you have as 64-bit integers. 64-bit integers only go up to 10 to the 19. There is no way that a standard integer type will work. Okay, but anyhow, let's ignore that for now. How do we even compute this? Forgetting about the other part. Okay, so there's a problem, but um, we'll worry about this later. So if this is the start and this is the end, what we're going to do, this is a fairly standard way of doing this kind of problem, is to compute the number of ways you can reach each spot from the start. And then, of course, if you compute the number of ways you can reach each spot, and you know that number of ways you can get to the end, then that's your answer. How many ways can you get from the start? Well, that's just one. So that's easy. It's just one. All of these are ones. There's only one way you can get to this spot, by either going strictly up or strictly to the right. Now, any other spot, you can come from that spot either by going to the right from a previous spot or up from a previous spot. And this would be 4, 6, 4, 5, 10, 10, right? 6 plus 4, 5, which is 4 plus. And you might, if you do this, you might quickly realize that this is what people call the Pascal triangle rotated, right? So this is just a Pascal triangle, but rotated so that this is now the top of the triangle. So, and the Pascal triangle just says, well, you add up these two. For example, you get the next one, and it's exactly why this looks exactly like, the binomial coefficient. It's not a surprise at all. But how do we incorporate? Let's say this is a mine. Well, whenever there's a mine, instead of computing this is 15, but what do? You just set it to 0, right? If there's a mine, then what ways to get here is 0. And then when you get to this point to compute this one, let's say this is not a mine, then what do? Well, you take whatever this is, so this is 20, and you add 0, so now there are only 20 ways to get there. So basically all you do is you just carry out the same computation that you normally do, except that when you see a mine, you set it to 0. And that's it. This, it's at most 128 each way. So 128 squares is not that much, 2 to the 7. So 128 squares, 2 to the 14. So what 2 to the 10 is about 1,000, 1,024, but let's say it's 1,000. So 2 to the 4 is about 16,000, which is nothing. So we fill up this square using this approach, always making sure that we traverse this, we compute this in the order that from bottom, one row at a time from left to right, so that we make sure that by the time we reach anything that we want to compute, the one on the left and the one below, it's already computed, and then you can just add them up. But there's still a problem. The problem is, what do we do with these huge numbers? So at this point, you have two choices. Either you try to figure out a way to deal with the big numbers by writing your own integer class. And if you go to my code library, which we showed you last time, there is a big integer class that you can paste in. Or for those of you that are not afraid to venture out of your C++ life, you could use Python, because Python integers are automatically arbitrary precision. It can be as long as you want. Of course, there's a penalty in performance if you're using really large integers, but because we're just adding numbers, it's not that bad. And that's what I'm going to do this time. Okay, so if you don't know Python, right, then maybe this is not going to make much sense, but it's never a bad idea to learn multiple languages anyway, so here it is. So the first thing is I read in all the data, and this is one way. I'm not a Python expert myself, but this is one way I can do this. Input basically reads a line, split it into multiple parts, and then for each one, convert it to an int. So that's a way to write this particular input. Here, this is a way to create a two-dimensional array from 0 to 128. So 129, because in Python, range of 129 is 0 to 1 less than that. So this gives me 0 to 128. Then I set the initial point to be 1, because that's exactly one way to get there from the beginning. And then I have a loop that loops through this range of x and y in the right order. And because I already set the initial one, I just skip it. I guess I could actually change this to set it to 1 instead of setting the 1 out here. But I guess in my mind, this is initialization, so that's what I did. I set it to 0 to begin with. Then if if it is a mine, so this checks if it is one of the two mines. If it's a mine, then I just continue to the next loop. Otherwise, I add the thing to the left, I add the thing from below, but only if there is something to the left. So this makes sure that I'm not reading out of bounds. This makes sure I'm not reading out of bounds. Now I could, if I want, do something a little bit sneaky and create my array one bigger to add a row and column on the bottom and on the left to be all zeros. And then I would only use, then that I don't have to check if I'm out of bounds because I made sure that there's no way I'm out of bound, and adding would only add 0. So I can just do this adding without actually ever bothering to check. Anyhow, at the end, I just print out the answer. And because this is Python, there is no limit. Well, there's no realistic limit on how big the integers can get. Of course, there's a limit if you run out of memory and so on, but 10 to the 79 is only 79 digits, so it's not going to use up that much memory. Okay, so that's that one. Okay, now the next one is something that could be extremely easy in some way, but I still want to show you this idea. Okay, so the problem says union find. Now, you may have heard of something called union find, and if you have, then this problem will be very easy. If you've never heard of it, then let's take a look. Okay, so you have a bunch of integer. You have n and q. N is the number of elements in the set up to 1,000,000, and q is the number of operations. Each operation, it's one of two types, asking if a and b, asking if the sets containing a and b are joined, and question mark a and b is asking whether a and b belong to the same set. Now, they actually did not tell you that initially every single set, every single element are in their own set. But anyway, in both cases, a and b are distinct integers between 0 and -1. For each query output line, yes, if they're the same set, otherwise say no. So if you see equals, you don't have to do anything, but you don't have to write any output. If you see question mark, you have to say, are they in the same set? So here at the beginning, 1 and 3 are not in the same set. Then you make 1 and 8, join 1 and 8. Then you join 3 and 8. So 1 and 3 are now indirectly in the same set. Okay, 0, 0, of course, it's always in the same set. You join 0 and 1, you join 1 and 2, you join 0 and 2, so 0, 1, and 2 are all in the same set. Although 0 and 2 joining them is redundant, because if 0 and 1 are in the same set and 1 and 2 are in the same set, then 0 and 2 are automatically in the same set. And then you ask if 0 and 3 are in the same set, and the answer is no. All right. So what we have, it's commonly known as dynamic equivalence relations. And if you have taken Math 2000, you probably know what equivalence relations means, meaning that x is always equivalent to itself. If x is equivalent to y, then y is equivalent to x. And if x is equivalent to y and y is equivalent to z, then x is equivalent to z. So that's the equivalence relations. And dynamic means that you can dynamically change the relationship. So maybe few things are not originally related to each other before, and at some point you can decide to make them related, and then everything will have to be updated to when you ask, are two things related? There's also a different name for this, sometimes called disjoint set. Okay, so you can put things into a set, group them together, and two things are equivalent if they belong to the same set. There's also, of course, the word union find. All of these words are in the literature. And the basic operations you can do is you initialize, of course, you should initialize n objects. So they are all in their own set. So everybody's separate in the original part. Then you can repeatedly do one of two things. Merge, depending on what literature you read, it can be called union, it can be called merge, two items or two objects. And of course, if you try to merge two things that are already in the same set, then you ignore the request. Also, you can say, maybe let me be a little bit more precise what you can do. Return a unique ID of the set containing an object. And this is often called a find operation. So what do I mean by unique ID? So if I call find on two things and they give me the same ID, then they're in the set. They're in the same set. If they come back with different IDs, then for sure they are not in the same set. So the unique ID is it's an ID that is unique to the set, and everybody in that set will give that ID. However, as you merge things, the IDs can change. Even the IDs of the set that is used can change. Okay, but at any one time, if you ask for the ID of two things, you can tell immediately whether the two IDs are the same, whether the two items belong to the same set. So if you go to the code library that I showed you before, there's something called union find, and it's an actual class that you would initialize how many. So you say n objects, and then you would call find, which will tell you the ID of the set containing x. Of course, x has to be between 0 and n minus 1. and then merge, which takes two objects and make sure that they're in the same set. Bool, it returns true or false. It returns true if there was an actual merge, and it turns false if they were already in the same set and there was no reason to merge them. Okay, and you could ignore that in this problem because you don't actually need to know if merging two things were really needed. You just need to make sure it's done. Now, you might want to know how this actually works. And one of the things I plan to do, apart from these problem-solving session, is to make a few videos on different data structures and algorithms about how they work. It's not completely required if you just want to know, if you just want to use these data structures and algorithms. But if you're interested, I'll be posting those kind of videos throughout the summer about how underneath these things all work. The important thing is, what is the cause of these things, right? Because you want a data structure where these operations are actually fast, right? If everything is, I don't know, linear time, big of n, and you have to do a bunch of operations, right? You have 1 million for n and you have 1 million for queries. If every operation requires linear time in terms of n, you're in a lot of trouble, right? 1 million squared, that's way too much. So what is the complexity? The complexity of everything to initialize n objects is order n. Okay, so that's not a big deal. But these things, what is the complexity of each merge or union, and what's the complexity of each find? This is a very difficult thing to answer. And in fact, understanding exactly why it's fast, I mean, if you actually look up how these things are implemented, you might say, yeah, I can see why it's fast. But actually analyzing it, it turns out to be a real hard thing. So what am I going to say? I'm just good. And in fact, the complexity is hard to even um, exactly state without a little bit more math. So I'm just going to say pretend they are constant time. Okay, so I'm going to use the word pretend. They are not constant time. But for all practical purposes, you can pretend that no matter how many objects you have to keep track of, these operations are effectively constant time, which basically means they are so fast that you don't even think about how slow they are. There's nothing that can be faster than constant time in terms of complexity. Again, I will stress that this is not true, but in practice, you can pretend that it's true. There's a couple of complications about what's going on, and when I actually make that video about how union find work, I'll talk about that. Okay, so what does that mean? That means that for our problem, the initialization part will have big of n, and for handling the queries, it'll be big O of q, because there are q queries to handle, and it's linear time. Okay, so you can pretend that this is, okay, so I'm going to put double quotes here because this is not, whatever I said is not true, but you must, as I said, you can pretend that it is. A slightly more accurate thing is to say that it's q plus n. But since you already have n anyway, so we don't have to worry about the plus n. So in any case, the point is that we can do this in roughly a million operations on both. And that's it. That is the entire problem. If you just take the class and then just stick it in here, and then you just process it, right? Union find n plus what? Why did I have n plus 1? Actually, I don't remember. Is it up to n, 0 to n minus 1. Actually, I don't know why I put n plus 1. You only need n. And then I just, if you see equals, I merge them. If you see question mark, I ask if defined, return the same ID, say yes or no. Now, this is actually something that I want to try. This I did this a while ago, and I don't actually know if the extra stuff that I need put in are necessary for this problem. Because if they are, then I definitely need to tell you what this extra stuff is. Okay, what was it called? Union. Fine. Okay, and I'm gonna get rid of this extra stuff. Let's see. Yeah, unfortunately, you need this. Okay. So what was it that I added here? There are two things I added here. Well, actually three. One that I haven't talked about yet. So in C++, because it's built on top of C as a predecessor, there are actually two distinct I/O systems that you can use to read and write stuff. And because they're two separate things, which is called stdio, and then of course there's IO stream. So stdio is from the old C language. Because they're two different things, if you were to, let's say, write something with, I don't know, write something with standard IO, and then later on write something with C++ IO stream, if they are not somehow synchronized and the buffers are not tied together, they could get all scrambled up, right? Because if you write something in one system, they don't send it out immediately normally because they buffer things. Then you send it to another system, and then everything got all mangled up. So normally, the input and output between the two libraries are tied together, the buffers and so on. And by tying things together, you get proper output if you do choose to use both. But that means that there are extra bookkeeping. And if you're not using the other version, the other library for input output, then maybe you can turn it off and save some time. When there's a lot of input and a lot of output, in this case, a million possible input and output pairs, doing all this explicitly might be too much. And this is a standard line, 2 lines, that says don't bother syncing up with the other one. Okay, we are only going to use C++ IO. Please don't bother. Save the time. I'm never going to use the other one. Now, is it safe to do that all the time? Well, in practice, unless you really, really need it, you probably don't want this because, if you're writing real production code, you do not know if any of the libraries that you're using are actually hidden inside using the other C library for IO, right? But because these are small programs that we write ourselves, we know that we're only using C++ IO, then we're safe to do so. The other thing, let me see if that make it. The other thing is that I use new line here. The normal way that most people do things is this. So let's see if that's acceptable or not. The difference is that when you use the \n, it just prints a character into the buffer, into the C++ IO buffer, and will go and read it. It'll go and write it eventually when it feels like it's has collected enough. They say its time limit exceeded. But when I put in the actual \n, so when I put the \n, it just fill it in a buffer. But endl has a special meaning. endl, it says, inserts a new line in character into the output sequence and flushes it. Okay, flushes it basically means that it must dump the output. Okay, it must dump the output to the device, whatever device you're writing to, and that defeats the purpose of buffering to basically make things more efficient by dumping to the actual device less often. Okay, so this can actually cause a slowdown as well because I/O generally are much, much, much slower than computation. So those are the three things, three lines, or these two lines, and then there's this little trick to make sure that we're not going to be slowed down by I/O. Now this is usually not necessary, but if you ever run into a problem where you have this problem, then you might want to think about this. All right. And the next problem, you're asked to compute a median of a bunch of numbers. If n is odd, then there's one right in the middle. If n is even, then it's the average of the two middle values rounded down. The problem is that the median values, in this case is the array that you're trying to compute the median of, is not a static one. You keep adding elements one by one, and at every step you're asked, please give me the current median. Right? So if there was only one static array and you just compute the median, there are many ways you can do this. For example, you can just sort the thing and look for the one in the middle, or you can do other things. But because this is continuously being modified, if you were to do this recomputation of medians every single time, let's say you sort everything every single time you add something and look for the middle, that would be inefficient. It would be too slow because you can have up to 10 to the 5, which is 100,000 numbers. Okay, this is also a problem with multiple. This is sort of an introduction to competitive programming, so there are multiple test cases. If you can solve smaller problems, then you can get a smaller number of points. But if you want to be able to get all the points, you have to be able to solve the biggest cases. Okay. So anytime that you have to play with dynamically changing data and then do some computation, you're looking for some kind of data structure that allows you to continuously update things. Now, but before we actually do this, let me show you that there is actually an algorithm in C++ that you can use to find the median. And then it's not just sorting, okay? So we look at here and okay, where is it? Sorting and related operations. So here we are. There's something called nth element, partially sorts the given range, making sure it's partitioned by the given element. So you can actually say, so nth element, you have to say, where's the range that you're interested in? and then, sorry, the range is first and last, and then the middle parameter, it's a parameter that points to the position that you want. So if you know which position you want, you can pass that in, and then you can get the median, or whatever position you want. If you want the biggest one, second biggest one, third biggest one, you can do that. Complex is apparently linear time, applications of comparator, and up to n log n swarm. So it's up to the basically up to sorting, okay? And the array of the vector. So for example, here's actually kind of like a median thing, right? So you have this vector. The median is basically the position from the begin plus half of it, and then just call it nth element. Now in this case, how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if the 10 things, so it doesn't really work for us because in our case, 10 things, we actually want the fifth and sixth thing together and then average it. But we can change that. Okay. But this only works, right, for one static array. If you don't want to keep adding elements in your array and then keep calling this, because that would be too slow. Okay, so there are a couple of ways you can do this. The first way, which I guess I don't know what people think about doing such things, is to use a G++ extension. It is a specific type of data structures that is only available in G++, which is a cloud in Caddis, but it is not part of the C++ standards. And these are called policy-based data structures. It's available in G++. It is non-standard. Okay, so it's not part of the STL. And there's no guarantee that if you use a different compiler, you can still use it. Okay, so what is it? Policy-based uses Policy-based data structures, blah, blah, blah. PBDS uses policy-based design, which allows you to customize a container's internal behavior by passing policies as template parameters. So you can decide, instead of using a set, or map, or whatever, where inside is in some kind of a binary search tree, you can actually change certain things and change how things internally are used. And one of the things that you can do, the most popular PBDS, it's called an order sets or order map or order statistics tree. And it allows two extra operations, which allows you to basically keep a binary search tree balanced and allows you to find the kth smallest element, or given a particular key, how many things are under smaller than x. So you can say what is the rank of that element. And then there are things that you can use to do this. There's also hash tables that are significantly faster than standard and order map. Anyway, then there might be other ones. But the most important one is this order statistics tree. So I just want to show you how this is used. Okay, so in order to use it, you have to include some extra things. So the bit/std++.h includes all the standard stuff, but does not include anything that's non-standard. So here's extension, C++ extension, and you must define this special namespace. And you have to define, which I use the type def. This is how you use an order statistics tree. I define the type OST to mean this. Now I use my tree is going to store pairs of integers, but in general, your tree can store anything. I'll tell you why I store pairs later. And um, RB tree tag means what is the underlying data structure you use. It's called red-black trees that I'm not going to talk about, but basically it's a certain kind of self-balancing binary search tree. This is a comparison operator you use to decide what is less than and bigger than in terms of keys. And then you have this thing called the tree order statistics node update, which says please keep track of stuff to allow me to look for keys by a certain order. Okay, so other than that, okay, so I use 64-bit sum because if you look at the problem, the sum of all the medians could be bigger than a 32-bit integer. I declare the tree. I keep reading numbers in. For each one, I insert the key, right, the number. Now, I'll tell you why I make this pair. So here, each number that I read in, I'm making it a pair including the number and the ID, basically the sequence number. Why do I do that? Because an order statistics tree, like most binary search trees, set or whatever, does not allow for duplicates. So if somebody give me two numbers that are the same, it will just basically ignore the second entry. And I don't want that. I need to keep all the duplicates. So by making it into a pair with a unique ID, I make sure that there are no duplicates. And I make sure that in a pair, the first element is the number that I want to sort on, because when I compare two elements I want as a pair, it always compare the first component, and if there's a tie, then it breaks tie with the second component. Okay, so once I insert it, then it's pretty straightforward. I have to be a little bit careful how to compute the indices, so you have to work things out. But basically, size is the size of the array at that point. The middle point is this, and then if it's odd, then this is the um, median. So I do tree.find by order median, and that returns a pointer or an iterator to that element, which points to a pair, and then I pick it apart and take the first component. If it's an even number, I do the same thing, but this time I have to take the two middle ones, so I have to be careful. The indices are mid and mid minus 1. I take them, I add them, I divide by 2, and remember that integer division is rounded down, so that's exactly what I need. And then that's all I do. Okay, so that's how you can use what is called an order statistics tree to continuously update, and you can also remove elements if you want, right? So I know that in this problem I'm only adding elements, but I can also remove them. Okay, so now what else can we do? What if you don't like this? What if you don't like using these strange data structures that are non-standard? Okay, instead of doing this, you could, I suppose, write your own binary search tree, right? But then you have to worry about balancing, and if you've ever learned about balancing binary trees and so on, it's always a mess, right? And then you have to deal with all of that stuff. So we would prefer to use something that's already there, if possible. Now, we only care about the median. We only care about the middle, right? So if I have a list of numbers, whatever they might be, what do I really care? I care about the thing in the middle. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so in this case, these are the two things in the middle. If this is A and this is B, let's say, All I care about is that these things are less than or equal to A in some order, and these things are greater or equal to B in some order. I don't care about anything else. And that's, of course, these two are my thing. If I now add another number, let's say that the number that I add is bigger than B. Well, what do? I stick it over here, right? And if I add something that's less than A, less than or equal to A, I stick it over here. But every time I add or, or things, if I add too many on this side, let's say I keep adding stuff because everything is less than A. Well, but now things have to shift because the middle, it's no longer here. When you have too many things over here, I have to rebalance. How do I rebalance? I need to shift this one into here, this one into this spot, and pick the biggest one into here. What if this part gets too big? Well, I got to shift this one into here, this one into here, and this one into here. The smallest one to shift, right? And then here you need to shift the biggest. That's all I care. All I want is to make sure that I can easily find the biggest one to shift if I need to. And here, all I want is I need to be able to find the smallest one to be able to shift into. And what that means is that I can have two priority queues. I'll show it like this because we know that, at least for those of you that know how priority queues are implemented, they are what we call binary heap. And one would be what we call, let's say, that's what I call it, the small half, first half, the small half, and the big half. And we will try and to make sure that these two are as even as possible. And this is going to be a max heap, and this is going to be a min. Actually, why don't I put the word max and min on top? The max is at the top, and this one is going to be a min heap. If these two things, we want to make sure that these two things, the sizes are either exactly the same, or so the size, it's either equals, or that the small half, it's one bigger. So maybe they're both 5, or maybe they are 6 and 5. Okay, that's the only difference we allow. Okay, if it ever gets out of balance, then we do something. Okay, so what do we do, right? If we have such a if we maintain such a set, such a set of priority queues, then if the current number of elements is even, so the sizes of left and right, first and second half, small and big half are the same, then the median you want is just the max of this and the min of that's averaged together, right? And if the bottom half, the small half, is one bigger, then the median is just the max of the bottom half. That's it. Okay, so now a new number comes in. What do? We can compare. If it's smaller than this one, we stick it into here. If it's bigger than this one, we stick it into the other one. If it's equal, if it's either equals to, I should say, if it's less than or equal to max, we can put it in here. If it's bigger than or equal to min of the right half, the big half, you can put it in here. What if it's right in between, right? What if it's, it's bigger than the max, but less than min? Doesn't really matter. Put it in either one. Okay. Now that you put it here, you check if the sizes are still okay. What can go wrong? It could be that you have 5 and 6 like this. It could be that you have 7 and 5 like this, right? In either case, once you have an imbalance, what do? In this case, for example, you need to move the 6 to here. So which one do you move? You pick the minimum in the priority queue. We move it and put it over here. And in this case, if it's 7 and 5, you need to move something from the small half to the big half. You take the maximum of the big half and move it to the other side. And that's it. Okay, so what's the complexity? We know that inserting and also moving things around like this, extracting the minimum and inserting things in a priority queue is all log n time. So every single move or every single step to deal with this insertion of one single element, it's log n time. You do it n times for each element, so it's n log n, which is definitely okay. Remember that this sorting one single time, it's n log n time, right? So somehow we managed to do this incrementally without sacrificing complexity of just sorting it once at the end. Of course, the constant is much bigger than just sorting one at the end, but it is still n log n overall. So I want to show you how I implement this. So I have two priority queues I call top and bottom. Again, the sum is here. And now I do have to be a little bit careful. So I compare the top with the thing that I just read in. If it's less than or equal to top, I push it to the left. Otherwise, I push it to the right. There are two things I have to be careful about. Priority queue by default, it's a max priority queue. So there are ways you can change it to bottom, that bin priority queue, with specifying different parameters by changing the comparison function to use greater than instead of less than, or I use the trick to negate what I push into a max priority queue so that it kind of keeps track of the minimum. But I have to remember that when I pull things out, I have to multiply by -1. Okay, so this is what I choose. The other thing is, don't just compare the top of the bottom half, because there is a possibility that at the very, very beginning, that you have an empty bottom, right? So you got to make sure that you don't crash on your very first iteration. Okay, I push that in. Now I check, right? If the bottom size, it's at least top size plus 2, meaning that I have that imbalance, I got to get rid of, I need to move something from the top to the bottom, right? Sorry, the other way. I need to move something from the bottom to the top. So I take the max from the bottom half, and move it to the top half, and then get rid of it. And then the other one is if the top size is too big, then I move it the other way, right? Again, remembering that when I pull it out, I have to negate things. And then after I move everything, I can just look up which one is whether I'm in the bottom, whether I'm in the even case or odd case. Now this looks weird because we remember that we're supposed to take the two medians in the middle, add them, and divide by 2. So why am I subtracting them? Because I remember that I pull things out, I have to negate things because I inserted things, I essentially inserted the negatives in the top half. So you got to be a little bit careful here, the way that I did it. But anyway, so here's another way of doing it without using some strange non-standard data type that's G++ provides. I give you two different ways. Both of them are n log n overall. But the most important thing is to realize that things are happening dynamically. So you need to use the data structure to help you. And in this case, because we don't care about sorting the whole thing, just making sure that the things in the middle are where they're supposed to be, we can use a priority queue to of two priority queues to keep track of the bottom half and the top half. Okay, last one. Last one, I'm not going to show you the code, but I'm just going to talk you through it. Okay, so this, it's called almost UnionFi. Okay, so this is almost like the UnionFi property we talked about before, but it is not. Um, okay, so you have a, I hope you know the beautiful union data, the UnionFi structure. You have to implement something similar but not identical. You need to write a collection of disjoint sets supporting three operations now. Okay, what can you do? One PQ union the sets containing P and Q. If they are already in same set, ignore this command. So this is the basic union find command, merge or union. Two, move the set, move P to the set containing Q. Okay, just P, not the whole set containing P, just Q, just P itself. And if P and Q are already in the same set, don't do anything. Okay, so this is different. Finally, return the number of elements and the sum of elements in the set containing P. Initially, the collection are n sets, each one by itself. Okay, so let's talk about how to deal with 3, which is to return the number of elements and the sum of elements in the set containing P, and then we'll worry about 2. Okay, so there are up to 100,000 of for n and 100,000 operations and so on. Okay, so forget about the move for now. What are we going to do in terms of we need the sum of the set and the size of the set? Now, one of the things that I did not say before is that when you call find, the ID that it returns is always between 0 to n minus 1. Okay, so the ID is actually one of the elements that are in that set. You just don't know which one. So how do we keep track of the sum and the size? Well, we could have a separate array of sum and size indexed by 0, 1, all the way up to n minus 1. And initially, right, you just set all the sizes to 1. And then the sum would just be the element, right? So let me just clean this up, my drawing a little bit. Now they tell you what the initial elements are, right? Oh, they don't tell you initially, but oh, of course they tell you it's 1 to n. So you can initially, well, I guess it depends on whether you use 0 base or 1 base. But let's say you use 0 base, then you would initialize this to be the sum 1 to n, right? And now find doesn't change any of this, but when you merge A and B, what would happen is that you would not only just merge them, but before you do, you look at find A, that will give you one ID, find B, that will give you another ID. If they're different, right? If they're the same, you don't do anything. So let's say that at some point, maybe you have, you know, a set of size 3 and a set of size 2, and the sum might be 10 and 20 or something like that. And this is ID 1 and this is ID 2. After you merge it, find A and find B will be the same. But the same as what? It's always going to be one of the ID 1 or ID 2. Okay, so you don't know which one yet, but you can check. But it's always going to be one of those. So let's say it's ID 2. So what do? You would then just add into this here, and now this number will keep track of the sum and the size. if you're confident, if you really want to, you can actually go and look into the data structure union find and maintain this inside, as opposed to trying to do that outside. It all depends on whether you're comfortable with modifying the existing data structure to also keep track of sum and size or not. If not, you can maintain these two arrays outside. Okay, so as long as you maintain the sum and the size, then it's okay. Yeah, you just look it up. And because these two, basically after you find the two, ID1 and ID2, and after you merge it to know which ID you actually merge to, you can just write it in constant time. In fact, if you don't care, you can actually just remember this is ID1 and ID2, figure out the new sum and new size, and just don't even bother checking whether it's ID1 and ID2 to merge to, just write both of them. And that's okay, even though this entry will never be used again. Okay, so once an ID disappears, it will never be used again in this union file. Anyway, some of that will require you to know the internal workings of this union find. So I'm just going to tell you for now that this is how it behaves. Okay, now the question is, what do we do when we have a set already? I don't know, maybe you have a set like this. So you know that the sum is 10 and the size is 4. And now you want to, and then maybe you have another set, 5, 6, 7, 8. So you know that the sum is whatever it is, 1326, and the size is 4. And now we want to move 3 into this set, let's say. The unfortunate part is the way that the union find data structure works, if even if 3 is the ID of the set, there's no easy way to remove the 3 from that data structure without destroying everything. And sometimes if the ID of this set is not 3, if it's something else, you can't even get that ID. You don't know what the heck is going on in there at all. There's no easy way to remove or break up as two sets. Okay, so in union find, you can do union, you can do find. There's no way to separate or undo a merge easily anyway. Okay, so what should we do instead? What we're going to do is we're going to leave it in there. We're just going to leave it in the set. Okay, you might say, well, okay, how does that work? Now, because we're maintaining this sum and size separately, we could just get rid of the 3. We can just subtract the sum by 3. We can just get rid of it. Okay. But if somebody later on say, I want to merge things with 3, well, am I going to be merging into here? Right? I can also, of course, just add this, but I'm not going to do that yet. Right? Because later on, if somebody want to merge things with 3, I need to be merging things into here, not the other one. So what am I going to do? What I'm going to do is that every time somebody wants to move 3 or anything, I am going to create a new element, okay? And I'm going to use that element to merge in here. So instead of saying I want to merge element 2 or 3 or whatever it is, I'm merging n. But n has this sum, the value of n here. So I would now have 5 and 29, and I'm going to merge in 3. But I need to know that internally, if somebody ever wants to use 2 as the index, I don't look at 2 anymore. I look at n. N is my real index. And this entry is still there just because it has to be maintained in my data structure. And that's essentially it. Every time somebody moves, I create a new item and then merge it in. And then I update these sum and size separately. Now, in my union find data structure, I need to actually initialize at the very beginning how many entries there are. I can't just say they're n because I could be creating new entries every time I move. But I know that there are originally n things. There are at most m operations. So even if all of them are moves, where each one of them needs to create an n element, the total number of elements I would need is n plus m. So I can initialize my union find to n plus m. And that's how I do this problem. Okay, so why am I using n plus m plus 1? Because I'm, instead of using 0 base like I did on the slide, I just use 1 base and just forget about the 0 entries to make things a little bit easier. And I decided to hack my union find data structure to include both the counts, which is the size, and the sum inside. I do that because I know how this thing works, right? So I initialize the first n items. So this is what the usual union find things. This is how big the set is, so they're all 1. This is a sum, which is just the element itself. And this index I is to keep track of for each item I, what is the real index in the union find data structure for that thing. So every time I actually do a move and create a new item, I have to update my index of that element to point to the actual current thing. And then the things that I could potentially create, I just set this count to 1, and then here, this is the standard union find initialization, but the sum currently is 0 because I don't know what values I'm putting, which ones I'm moving. Okay, so find and find help, this is exactly the same as code as before. Merge, I update the sum. So res1 is basically the ID that will be used after the two things are merged. So I basically just add the other one into the sum and the count. So move is the one that's interesting. I look at the ID of the two things the X that I'm moving into Y, and nothing will happen if they're the same because there's already there. Otherwise, I remove from the original set the count and also the sum, remove X. Then next is actually next is actually the first item, the first index that I use in my list of new things to create. Okay, so n plus 1 is the first ID that I would use for creating things. So I set the ID to point to this new entry. I make the sum to be the element that I'm just adding now. I update the next so that the next time I need another one, it will move up by 1. And now I call merge. So I'm merging the new entry with the old one. And then the rest of the code is pretty straightforward. I read in the command and then P. Why don't I read a P and Q? Because type 3 only has P and no Q. So if it's this case 1, it's just a normal merge. Otherwise, I call move. Otherwise, I print out the count. But only after I find the ID of the set containing P. Okay, so this one, it's a I don't know if I would call it basic union find problem. I mean, they even tell you union find, but you need a little bit more work to try to figure out what to do with this move. And this is how I deal with this. Now, there is something that I just want to kind of say, and it's something that I don't know too much about myself. It's much harder. It's perhaps a little bit unrelated to this. What is this? Get explanations. You can. Okay. I don't know if I want. Sure, continue. Do I want to? Okay, so a persistent data structure is something that um, I kind of, I kind of mentioned this. Specialized data structures that always preserve the previous historical versions whenever they're modified. So instead of performing mutations in place like standard data structures, any update creates a new version of the structures while leaving the old versions fully intact and accessible. So somehow you can undo stuff and go back to previous versions. Of course, you might say, well, why don't I just make a copy every time? Then, of course, that's really, really bad in terms of performance. And so there are somehow there's these things called structure sharing, meaning the new version reuses as much of the original allocations and modified memory and pointer nodes as possible, and this makes them fundamental tools in functional programming paradigms and concurrent system. So, for example, if I want to do one undo step after I moved it the way that I did, I could simply go back to where it used to be and then do a little bit of change, and I can undo a move. Of course, if I have move and then merge after that, then that might make things a little bit harder. But if I just have a bunch of moves, if I just have a move, I might be able to undo uh, by doing some. And there is a lot of difficulties to deal with this sort of stuff. Um, and I think what is persistent union find data structure? There is actually one that allows you to track a collection of disjoints across its entire history, allowing you to query or even modify past connectivity states. But anyway, this is a much harder thing. So anyway, I don't want to say too much more, uh, but you can see that persistent data union find complexity is log of n or log of square n. Space complexity is a little bit more, and so on. Um, and then the standard union find. Um, okay, so time complexity. It says amortized big O of this alpha n, but then it has the word nearly instant, which is what I said you can pretend it's constant time. But what the heck is amortized mean, and what the heck is this alpha? Uh, I'm not going to talk about now. Okay, so as I said, I'm going to start making some additional videos about data structures and algorithms and the internal workings. They're not completely necessary for solving these problems if you just use my code library, but they could be just useful for education, but or if you ever need to, run in a situation where you need to actually go in and modify the data structure to do something else that is similar but not quite, then knowing internally how things work would be quite useful. Anyway, I think that's the end of the video today, and we'll see what happens next week.